In the next two lectures, we're going to talk about several reduced form methods that are used across many fields, including my own field, industrial organization. The three common methods are regression discontinuity, difference in differences, and instrumental variables regression. I'm going to focus on the former two, as I expect you are all well versed in IV regression. For reasons that you will see shortly, regression discontinuity typically uses cross-sectional data sets, whereas difference in differences typically uses panel data sets. So let me give an example of regression discontinuity to motivate it. Suppose that you want to know what the impact is of a new school building. The idea is that the new school structures can impact student outcomes in a variety of ways, from improving the learning environment to attracting teachers and parents who care more about student outcomes. However, let's take a step back and think about the mechanism of how a new school gets built. A new school needs funding, which in many cases voters need to approve. Hence, a new school only gets built if 50% of voters approve it. However, school districts with a large share of the population supporting a new school building might also support the new school in other unobserved ways, and these other ways may independently impact student outcomes. To see how this confounds our results, consider the following graph. Here is a graph that shows some hypothetical measure of student performance on the vertical axis, and the fraction of voters who voted to approve a new building, a new school building, on the horizontal axis. A naive way of estimating the impact of a new school building would be to simply look at the average difference in outcomes among the two sets of school districts, one which built a new school and one which did not. This difference is illustrated on the graph using two horizontal lines, and the implied impact of the new school is the height difference between these two horizontal lines. However, this does not give us the causal impact of a new school building. The difference in averages also reflect these other factors that are independent of getting a new school. So how does regression discontinuity address this? Let's start with a story that illustrates the idea. Suppose a new school only gets built if at least 50% of the voters approve it. Imagine two towns, one in which 49.99% of voters voted for a new school building, and another town where 50% of voters voted for it. Clearly, these two towns are very close in the percent of voters who support a new school building, and therefore, it is likely that these two towns are similar in support for other measures that independently impact student outcomes. However, these two towns will have very different outcomes as it pertains to a new school building because only the latter town surpassed the 50% threshold needed to fund a new school building. While the towns look nearly identical, only one gets a new school building. This story is nice, but there is a problem. It requires many schools right near the voting threshold. If there aren't very many right near the threshold, then to reduce noise of estimates, one would need to include schools further from the threshold, say schools where 40% to 60% voted for it. When we do that, then we're starting to get the districts that actually look rather substantially different in terms of the support that they have for their schools. These towns are not going to be the sort of apples to apples comparison on these other confounding factors. So how does regression discontinuity address this limited data issue? In the simplest form, it involves fitting a linear regression line on each side of this threshold, where the treatment of interest changes is switching from 0 to 1. Specifically, one can project student outcomes for towns with 50% vote share, but do so twice, once using the points on the left side of the threshold, and once using the points on the right side. We are thus projecting outcomes for districts with 50% of the population voting for a new school, both for districts with and without a new school building. This allows one to incorporate more data, but still uses a method analogous to the simple story that I gave earlier. So to do this, one could try doing this using a simple or single regression if you're willing to assume that the slope is the same on both sides of the threshold. In this slide, you can see an example. Y is equal to alpha, a constant, plus beta times the vote share. The latter terms account for the how student outcomes change as a greater share of the population votes for it. Right? Typically, we assume that this relationship is smooth. Next, the third term, which is gamma times an indicator function for the vote exceeding 50%, captures the jump at the threshold in the outcome variable where the new school gets built. So that third term is our estimated impact of the causal impact of the new school building. Okay? That's pretty simple. You can extend it somewhat. One could fit two linear regressions, one on each side of the threshold. One could use nonlinear regressions, thus placing less functional form restrictions on the model. You could even do it non-parametrically. If you do it non-parametrically, however, you do want to make sure that you use a local linear regression rather than a kernel regression, because the kernel regression is biased at the extremes, implying that the regression discontinuity estimates will be biased as well because we measure those at the extremes, that is at the threshold. In any case, after estimating these regressions, you can compare the projection from the points on the right of the threshold with the corresponding projection using the points on the right. Sorry, it's a projection from the left and projection from the right. Now, you do want to be careful when you're doing this and make sure that what you're doing makes intuitive sense. In this example, I fit two different linear regressions, one on each side of the threshold. Note that the one on the left has a negative slope and the one on the right has a positive slope. A difference at the threshold is apparent, but I don't think that it is necessarily real. It doesn't make sense that you would see such different regression slopes on each side of the threshold. So you just want to use some common sense when you're doing things like this. So, in this example here, it would imply that as the share of the population voting for a new school increases, it actually reduces measures of student performance up until the point where you reach the 50% vote share threshold. After that threshold, increases in the share of the population voting for it increase the measure of student success. This just does not make sense. We would normally think that the larger the vote share supporting a new school, the larger the share of the population that cares a lot about schools. Okay, so we would actually expect a positive regression line on both sides of the threshold, even if they're not the same slope.